For the 13th and final lecture, we're going to talk about amines, the functional groups containing nitrogen, and some of their properties and reactions. So amines are organic derivatives of ammonia. Ammonia is NH3, so any nitrogen, NH3 like this, that's connected to a carbon will be called an amine. There's a special kind of subclass of amines called alkaloids. Amines are really common in biological functions, and alkaloids are those biologically active amines. Most alkaloids are synthesized by plants kind of as secondary metabolites, and which are basically metabolic byproducts. Some alkaloids are often used medicinally, but all alkaloids are toxic and they'll cause death in large enough quantities. Just as a side note, the Greeks used an alkaloid called S-conine to kill Socrates, but if that high enough doses, morphine, nicotine, or cocaine would have served equally well. So these are some examples of amines. This is S-conine. This is dopamine, a neurotransmitter. This is epinephrine, an adrenal hormone. You'll notice that all of these have these tetrahedral nitrogens, N bonded to 3 groups and a lone pair. Some other alkaloids, these are all metabolic byproducts of plants. We have cocaine, which is found in cocoa leaves, nicotine and found in tobacco, mescaline is in peyote cactus, morphine is found in opium poppies. They're also often vitamins, like nicotinic acid is a vitamin, peroxidine, vitamin B6, and histamine dilates blood vessels. Also notice the extreme diversity in structure between all these molecules. There's not a single pattern that all of these follow. A lot of them will have aromatic rings like pyridine or benzene. Those aromatic systems show up a lot because they're particularly stable. It has no other relationship to their activity, only keeps them stable and makes them long-lived. Amines, like ethers, have a common naming system and a more systematic IUPAC naming system. Common amines are named either as primary amines, secondary amines, or tertiary amines by means of what their alkyl groups are. So here's an amine with an ethyl group, so that's ethylamine. Here's an amine with 2 isopentyl groups, so this is diisopentylamine. Here's an amine with 2 ethyls and a methyl, so this is diethylmethylamine. This is tetrabutyl ammonium chloride. The N plus, the quaternary nitrogen, is an ammonium. So this is tetrabutyl ammonium, that's the 4 butyl groups. Tetrabutyl ammonium chloride. Cyclohexyl dimethylamine, this is a tertiary amine, 3 R groups on it. Benzylamine has a benzyl group on it. Notice that the nitrogen is connected to the benzylic position. And then diphenylamine, this is a secondary amine. So primary amines have 1 R group on the nitrogen. Secondary amines have 2 R groups on the nitrogen. Tertiary amines have 3 R groups on the nitrogen. Amines have an enormous diversity in structure, and as a result of that, they have an enormous diversity in naming. Here are some non-systematic names, although a lot of them are now employed in IUPAC anyway. But these are non-systematic names of amines. We've got aziridine, pyrrole, pyrrolidine, imidazole, indole. This is purine and pyrimidine. You might probably recognize purines and pyrimidines from the DNA bases. Here's piperidine. Here's pyridine again. Aniline, 2-ethyl aniline. So you could say orthoethyl aniline. Remember, we talked about aniline being the NH2 coming off of a benzene ring. So yeah, I don't expect you to know these particular non-systematic names. For example, I don't expect you to know how pyrrole works or the numbering for imidazole or for indole. These are here for your reference. It's at least there so you can maybe be familiar with them. You say, oh, I remember pyrrole, that's a cyclic nitrogen compound. Or I remember pyrrolidine is different from pyrrole because pyrrolidine doesn't have the conjugated double bonds. things like that. As long as you can be familiar with them, that's probably all this is good for. As far as IUPAC systematic naming goes, the generic formula for amines are alkanamines. So we're going to find the longest carbon chain containing the nitrogen. We're going to name that as an alkanamine. We're going to number the substituents from the carbon bearing the nitrogen, and then short chain substituents on the nitrogen get labeled as N-alkyl. So this is a 4-carbon chain. Butanamine, it's 2-butanamine. Here's a 3-methyl 1-butanamine. Again, the nitrogen is on the 1 here. Nitrogen is on the 2 here. So the nitrogen will be on the 1, the methyl's on the 3. Here's a 2-butanamine with an N-methyl. The nitrogen has essentially the sec-butyl group and the methyl. You could call this sec-butyl methylamine, but the IUPAC name would view it from the longest carbon chain. So it's a butanamine with an N-methyl. Here we've got 4 methyls off of our chain. We've got 6 carbons, so it's a hexanamine. It's a 3-hexanamine because the nitrogen is on the 3. But then our methyl groups are on the 2 and the 4 and 2 on the N. So it would be 2,4-NN tetramethyl 3-hexanamine. Of course, you can split the root, 2,4-NN tetramethyl hexan 3-amine. Some structural properties of amines: they are polar. They are potentially hydrogen bonding if they have hydrogens on the nitrogen, meaning they are secondary or primary amines, therefore they are hydrogen bonding. They are almost always planar or tetrahedral. Nitriles are the exception. They are linear, they're sp hybridized. Here's an example. We've learned about trigonal pyramidal shapes for something with 3 bonds and a lone pair. It's not quite tetrahedral, it's 107 instead of 109.5. Notice that as we move from hydrogens on our nitrogen to methyls on our nitrogen, our bond angles expand from 107 degrees to 108 degrees. Of course, that's because of repulsion from the bulky methyl groups that are not present in the smaller hydrogens. Amines are usually polar because the nitrogen is an electron withdrawing group. It's a sigma withdrawing group. So in the trigonal pyramidal structure, you have all the dipoles pointing towards the nitrogen and then more electron density on the lone pair. That gives us an overall dipole moment from the R groups where it's positive towards the N where it's negative. Here's an example of hydrogen bonding where you have a donor with the hydrogen and an acceptor with the lone pair. Of course, that is possible as long as you have a hydrogen on your nitrogen. Tertiary amines cannot hydrogen bond unless there is a donor present, unless there's a secondary amine somewhere, or for example, water can be a donor. So tertiary amines can only accept hydrogen bonds. So if you have a pure tertiary amine, it will have a lower boiling point than a pure primary or secondary amine, despite having a higher molecular weight. So something that's kind of fun about amines is that a tetrahedral amine that has 3 different substituents and then a lone pair is technically non-superimposable on its mirror image, and it appears as though the nitrogen would be a chirality center. Again, think about the nitrogen with its lone pair in 3 different groups as having 4 different things coming off the N. Just like a carbon with 4 different things coming off the carbon, with 4 different groups, that would have a mirror image. The problem with nitrogens is that the lone pair can invert. The lone pair can actually tunnel through the nitrogen and invert the amine in a way that would not normally be possible if that was a normal bonded atom. Electrons are very weird. They behave much in line with quantum physics, and as such, they have superposition of states. So the lone pairs can be on one side of the nitrogen and on the other side of the nitrogen simultaneously. That's how tunneling works. Basically, the nitrogen electrons can appear up here, and the very next instance, they can appear down here. Depending on how you observe it, will change the chirality of that nitrogen. Now, since it's invertible, it's not chiral. You don't have a left-handed form or a right-handed form. You have an interconvertible form. So Amines appear to be chiral, but they are not. There are some exceptions to that. For example, there are some chiral amines that cannot invert or racemize. First of all, amines whose chirality does not arise from the nitrogen itself. Be careful, just because the chiral carbon has a nitrogen on it does not mean that that chiral carbon can invert. Here, that carbon has 4 bonded groups. Before, on the previous slide, we were talking about specifically where the nitrogen would appear to be the center of chirality. Quaternary ammonium salts can also be chiral, a methyl, an ethyl, an isopropyl, and the phenyl, and as such, those 4 dissimilar groups could be arranged in a left-handed form or a right-handed form. Because none of these groups are electrons, you don't get that inversion. Even with the ability to technically invert, many amines whose geometry forbids that planar transition state will not invert. So for example, in this 3-membered cyclic ring, where the nitrogen is one of our participants, notice that we've got 4 dissimilar groups. We've got the ring carbon with the 2 methyls, we've got the ring carbon with the 2 hydrogens, we've got the methyl, and we've got the lone pair. That nitrogen actually cannot invert because the strained, rigid structure of that ring prevents that intermediate transition state that's required for that inversion. Amines are nucleophilic and they are basic under most conditions. You can use the lone pair on a nitrogen as a nucleophile with some appropriate electrophile, like methyl iodide, for example. You make a nitrogen carbon bond. Amines can also be basic. Instead of using the lone pair as a nucleophile, it can use the lone pair as a base to grab an H plus off of some protic acid, displace the conjugate base as an X minus, and we have a protonated amine. So we can alkylate amines using alkyl halides. We can protonate amines using protic acids. Now, in terms of bases, we often refer to a pKb. pKb is 14 minus the pKa. So what that means is that strong bases will have low pKbs, the same way that strong acids have low pKas. Most amines have a pKb of around 3 to 5, meaning that their pKa is 9 to 11. Substitution on amines increases their basicity because hyperconjugation from the neighboring methyl groups or alkyl groups onto the positively charged nitrogen can stabilize that positively charged nitrogen. For example, if we look at ammonia reacting with water to remove a proton and to make ammonium and hydroxide, the positive charge on this nitrogen is not stabilized by anything in particular. If we compare that to methylamine and we do a proton transfer from water, we get the protonated methylamine, and that N plus is stabilized by hyperconjugation from the adjacent methyl group. That stabilizes the product, stabilizes the conjugate acid, which means the base is stronger. It moves the pKb from about 4.7 to about 3.4. That's slightly less than a factor of 10. There are, of course, exceptions to this. Remember, when we looked at aromaticity of something like pyrrole, pyrrole is aromatic because that lone pair can be placed in a p orbital and be delocalized around the ring like all the other pi electrons. That means that protonation at that site, we break our aromatic ring. We lose our fully conjugated system if we protonate at that site. The result, of course, is then that the nitrogen simply will not use its lone pairs to protonate from something. They will hold on to that lone pair and use them exclusively to maintain their aromatic state. The Kb of pyrrole is extremely tiny, 10 to the negative 15. Remember, a low pKb is a strong base, but a low Kb is a very weak base. This has essentially no forward direction. This is basically 0, 10 to the negative 15, which means that our equilibrium has no product. On the other hand, something like pyridine does not need the lone pair on the nitrogens to remain aromatic. It is aromatic as a result of the 3 pi bonds in the ring that are fully conjugated. That lone pair sits perpendicular to the p orbitals. It can't even mix with them if it wanted to. So because it's sp2 hybridized in the sp2 orbital, it is not part of the aromatic system, and the nitrogen is free to use it without breaking the aromaticity of the ring. Now, we can compare that pyridine, which is the conjugated system, to piperidine, which is a aliphatic system. And now the hybridization of the lone pair goes from being sp2 as in pyridine to being sp3 in piperidine. Notice the dramatic difference in pKb. Piperidine is a much stronger base than pyridine is, even though both of these lone pairs are free to react. The reason that's the case is that the sp3 electrons are held much farther out from the nucleus. Remember that as we increase s character, the electrons are held much closer to the nucleus. So these lone pairs, being in 33% s character orbital, sit very close to the nitrogen and are not as likely to be donated. Here in the 25% s character orbital, the electrons sit much farther away from the nitrogen and are not held as tightly. That is the difference of about 10 to the 6th power, about 1,000,000 times more basic as piperidine than pyridine. And of course, from pyridine to pyrrole, pyrrole isn't basic at all. So you go from being not basic at all for an aromatic system to being relatively basic for an sp2 system to being quite basic for an sp3 system. Pyridine's kind of interesting. We've seen pyridine before. This was pyridine. It's basically a benzene ring where one of the carbons has been replaced with a nitrogen. Pyridine is kind of interesting because although it is aromatic, it doesn't behave like benzene does in an aromatic substitution reaction. Rather, pyridine resembles a strongly deactivated benzene. Imagine that you've got a benzene with a bunch of deactivating groups on it. It's going to be very difficult to use that benzene ring as a nucleophile in an EAS reaction. It's so deactivated that the Friedel-Crafts reaction fails completely, and other reactions that add substituents to the ring require really strong conditions. Here's why. If we look at pyridine and we try to add some group to it, some electrophile to it, we will end up with an intermediate that has no octet on the nitrogen. This is a very bad type of sigma complex. Because of that, attack at the ortho, the 2 position, or the 4 position, the para, is not observed. Just like a deactivated ring, we go meta. Addition to a pyridine goes meta. That avoids forming the nitrogen that's missing an octet. So just like a deactivated benzene goes meta in future additions, a pyridine goes meta in all of its additions, if they even work in the first place. Now, we're going to finish the chapter with a handful of slides on 6 major reactions. I kind of call these the big 6. Sometimes you omit one of them. They call it the big 5. But I call these the big 6 reactions in amines. Pretty much there are 6 reactions that you need to know involving amines, and the rest of them are unimportant for the most part. The first one is the Hofmann elimination. Finally, after all these weeks, we've come to the Hofmann elimination, which gives us the Hofmann product in an elimination that forms a pi bond. Remember when we learned about E1 and E2, we learned about the Zaitsev product that gave us the more substituted double bond. And we said that the less substituted double bond is called the Hofmann product. I said because it is formed by the Hofmann elimination. I said we'll eventually at some point get to the Hofmann elimination. Here we finally are at the Hofmann elimination. The Hofmann elimination involves elimination of a quaternary amine. The quaternary amine favors formation of the less substituted alkene product, which of course we call the Hofmann product. So This involves what we call exhaustive methylation. If we've got some primary amine here, R NH2, and we use a huge excess of methyl iodide. Methyl iodide is usually the methylating agent of choice. What will happen is the nitrogen will add 3 times to the methyl and displace the iodide. So imagine the N attacks the methyl, kicks off the iodide, the I comes back and grabs the extra H. The N adds to another methyl, kicks off the iodide, the I comes back and grabs the other H. Then the N adds to another methyl, displaces the iodide. There are no hydrogens left, so we are stuck with the over methylated or completely methylated nitrogen. This is a quaternary amine with an R group and then our 3 methyls that we just added. It is that quaternary nitrogen that forces the Hofmann orientation because of the fact that the nitrogen with the trimethyls on it, this quaternary amine, is so big and bulky, it blocks removal of the hydrogen from the Zaitsev side and only gives access to the Hofmann side hydrogens. That mechanism proceeds just like E2, except that, again, the side that would normally give the Zaitsev product is not as accessible as the side that would give the Hofmann product. So we end up getting the double bond, but not in the Zaitsev position. This is guided by sterics. Here's an example where we took 2-butanamine, we methylated it, so we have this trimethyl ammonium group. Notice that if we remove the green hydrogen, that's a secondary hydrogen. If we remove the blue hydrogen, that's a methyl hydrogen. The blue hydrogen is more accessible than the green hydrogen. And the ammonium group blocks accessibility to both of these. And it turns out that it blocks the green enough that it does not get removed, but does not block the blue enough for it to not get removed. So our elimination is 95% Hofmann. We're going to remove the more accessible hydrogen, and we're almost never going to remove the less accessible, which is now not accessible at all, hydrogen, which would normally give the Zaitsev product. 95-5 in this method. Remember when we did E1 and E2, the book showed you that using a big bulky base like T-butoxide could sway the Hofmann product a little bit more. Normally we got like 70% Zaitsev, 30% Hofmann. And the book said that if you use a big bulky base, you can maybe get 60% Hofmann and 40% Zaitsev. In the Hofmann elimination using the quaternary amine, we get 95% Hofmann. So this is why we want to use this method if we want the less substituted amine. Looking at the Newman projection, you can kind of see why these 3 hydrogens over on the Zaitsev side are way more accessible than the hydrogens in the green group here. I made a graph showing the inaccessibility of the H's by the base. Without the N-trimethyl quaternary amine, we get Zaitsev elimination because they're both accessible. If we remove the secondary, we get the Zaitsev product. If we remove the primary, we get the Hofmann product. Since both of them are accessible, we always will get the Zaitsev. When we add N-trimethyl, we end up increasing the inaccessibility of both hydrogens, and we increase them enough that the secondary no longer is accessible. We cross some threshold where the hydrogens that would give rise to the Zaitsev product cannot be removed anymore. And so the only hydrogens that can be removed are the Hofmann elimination hydrogens. The second reaction in the big 6 is called reductive amination. This takes a ketone or an aldehyde. We react it with either a primary amine, a secondary amine, or a hydroxylamine. And we produce either the oxime in the event that we use hydroxylamine. We make an imine, an N-substituted imine, if we use a primary amine, or we get this quaternary iminium salt if we use a secondary amine. From that iminium ion or the imine or the oxime, we will do a reduction, usually with something like lithium aluminum tri-T-butoxyhydride. Here we have sodium triacetyl borohydride, one of our reduction agents that has only one hydride on the structure, will reduce the oxime or the N-substituted imine or the iminium salt by adding an H- at the carbon. Adding an H- to this carbon displaces the electrons onto the N. They get protonated. We end up losing our OH as water. That gets us a primary amine. Here, if the hydrogen attacks the carbon, we displace the electrons onto the N. Protonated, we get a secondary amine. Here, we add a hydrogen to our carbon, displace the electrons onto the N. We get a tertiary amine. We've gone over the mechanism of formation of the imine or the oxime from the ketone or aldehyde. Those notes are in previous lecture slides, and they're also on notes pages that I've added to Canvas. So reductive amination, we can make primary amine, secondary amine, or tertiary amine starting from a ketone or an aldehyde. We just have to choose the appropriate amine derivative to work with. A third reaction is similar. Reaction 3 of the big six is called acylation reduction. If we take an acid chloride and use ammonia as our nucleophile, this would be a nucleophilic acyl substitution, SNAC. We would get the amide. We can do that if we use ammonia, we get a primary amide. If we use a primary amine, we get a secondary amide, sometimes called an N-substituted amide. Notice our N has two R groups on it, the R prime and the carbonyl carbon. If we use a secondary amine, we will get the NN di-substituted amide or the tertiary amide. This will not work with a tertiary amine. Try to work out a mechanism, you'll find out why it doesn't work with a tertiary amine. But once we've made the amide, we can simply reduce the amide to the amine. And again, we looked over this mechanism in the amide section of the carboxylic acid derivatives chapter. We can reduce amides to amine using lithium aluminum hydride. That'll get us a primary amine, secondary amine, or a tertiary amine. We can very precisely control what the nature of our product is. We have to just choose the appropriate ammonia derivative. Reaction 4 is called the Gabriel synthesis. This is kind of a fun reaction. It starts with phthalimide, which is this guy right here. Sometimes this is sodium phthalimide paired up with a sodium, or lithium phthalimide paired up with a lithium. We take the phthalimide, and this nitrogen is a nucleophile. We can introduce it to an alkyl halide, and we'll alkylate the phthalimide. That will get us an N-alkyl phthalimide. That reaction, then if we add hydrazine, we get what's called a phthalimide hydrazide. And look what happens. The RNH2 pops off. This R group that was on the nitrogen pops off of the phthalimide ring. And we have made exclusively a primary amine. This ensures that we get a primary amine. If we want to start with nitrogen and put an R group on it, it can be really hard to control getting dialkyl or trialkyl or tetraalkyl derivatives. This method using the Gabriel synthesis ensures that we get a primary amine. An alternate cleavage, instead of making the phthalimide hydrazide right here, we can make this diacid anion. We can take our alkylated phthalimide, add 2 equivalents of hydroxide. That will convert the amide into the carboxylate. And in this case, we've got a dicarboxylate because this is kind of a diamide. And that, in the same way, dislodges our primary alkylated nitrogen. So either using hydroxide to get the dianion from the acid, or using hydrazine to get the hydrazide. Either way, the result is that we dislodge our N with our R group that we put on in the first place. Another reaction of amines named after our old friend Dr. Hoffman is the Hoffman rearrangement. And this converts an amide, say R C double bond O NH2, into the amine RNH2. It doesn't simply reduce the carbonyl away, it actually dislodges the CO carbon. Here's how it works. We'll start with a primary amide, and we'll use a base to remove one of our alpha hydrogens. we get a deprotonated amide, which is of course resonance stabilized. We'll add Br2 to this. And what will happen is we will brominate our amide. This is an N-bromoamide. This is the same mechanism that you might see in base catalyzed alpha halogenation. Now, putting the bromine on our alpha position serves a couple interesting functions. First, it makes the other hydrogen that much easier to remove. It makes it more acidic because the resulting anion is stabilized by the bromine. The bromine can withdraw electron density away from the negative charge. This will then undergo a rearrangement. The electrons will come down off of the O, and in order to make room for that additional bond, the R group on our carbonyl carbon will migrate to the nitrogen, and in doing so displace the bromide. So the bromide again serves two functions. It first of all makes the second alpha hydrogen more acidic, favoring formation of that negative charge, but then it serves as a leaving group to make room for our alkyl group when it migrates. So that makes an O double bond C double bond N R. That's called an isocyanate. Then our hydroxide will add to the isocyanate on the carbonyl carbon, displace the C O pi electrons onto the O. That gets us another resonance stabilized intermediate here. This is basically a deprotonated form of carbamic acid. If we reprotonate from the N- site, we get carbamic acid, which is the C double bond O with an OH on one side, so a carboxylic acid on one side, and an amide functional group on the other side. Carbamic acids tend to lose carbon dioxide spontaneously. So here's our decarboxylation reaction. We'll take base, deprotonate our acid. That should not be a surprise. That gets us the deprotonated carbamic acid. These electrons will come back down off of the O, make carbon dioxide, O double bond C double bond O. That will fall off, put the electrons back onto the N, gives us an N-. We've now dislodged our carbonyl carbon, and we can eventually reprotonate our N from water, and that gets us our amine. So this is, again, not quite the same as a reduction of amides. Reducing amides keeps the carbonyl carbon in place and replaces the double bond O with two H's. This actually, again, dislodges that C double bond O, and it does so as carbon dioxide. Very cool reaction called the Hofmann rearrangement. Now, there are lots of ways to oxidize amines. We can go from a primary amine to a hydroxylamine. That's an oxidation step. We can go from the hydroxylamine to the nitroso group. That's another oxidation step. We're going from 0 bonds to O to 1 bond to O. Now in the nitroso, we've got 2 bonds to O. We can do another oxidation step to make 3 bonds to O. That's a nitro group. We've seen nitro before. There are many oxidants that can accomplish these transformations. Things like peroxides, permanganates, and chromates. But in the case of amines, oxidation is difficult to control, and so mixtures almost always will result. If you start with a primary amine and you mix it with some oxidizing agent like potassium permanganate, you're going to get a mixture of hydroxylamines, nitrosos, nitros, all kinds of things. To make matters worse, these mechanisms of oxidations are not well known, partly because there are many reaction paths, and a lot of those involve radicals that are available. So since we don't understand the mechanisms well, we don't know really a lot of, say, foolproof ways to control the oxidation, to go from a primary to a hydroxyl, or from a primary to a nitroso, or from a hydroxyl to a nitro, instead of a nitroso, for example. So don't worry too much about oxidation of amines, because they're not real neat reactions. They're quite messy and they're not well understood. But one thing that we do know is how to oxidize tertiary amines reliably, because you can only go one oxidation cycle on a tertiary amine. and that is to add an oxygen in a single bond format to our nitrogen. We can do that with hydrogen peroxide or some peroxy acid. That will turn the tertiary amine into a tertiary amine oxide, this N plus O minus. This is involved in the cope-elimination. This is basically side-step elimination of a hydroxylamine. Look what happens. Once we take our tertiary amine and make the tertiary amine oxide, that oxide O minus will tend to grab an adjacent hydrogen. Those electrons from the hydrogen will fall in to make a pi bond, and the leaving group will be the N plus. Notice that the group that we lose here is our N-dimethyl OH, so a dimethyl hydroxylamine. That is basically our leaving group. What's kind of fun about this reaction is that the leaving group acts as the base before it leaves in the first place. There is a stereochemical requirement of this, and that is that we need a syn conformation, meaning that the N plus and the H that get removed have to be syn. Notice that if this H is pointed in the opposite direction, the O minus will not be able to grab it. If we had only an H down here, our O might not be able to grab it. So a syn conformation is required, not anti. This is not an anticoplanar rearrangement, meaning that this is not technically an E2 rearrangement or an E2 elimination. We've used diazonium ions before. We can make a diazonium salt from a primary amine. This is that O-No arrangement. Sodium nitrite plus HCl makes nitrous acid. That was HONO, HNO2, HONO. That's our O-No reaction. Remember, hot or cold O-No. That converted a primary amine into a diazonium salt. And that diazonium can be used in a lot of different ways. I'm going to skip over the mechanism. It's not particularly important. You can read it and try to understand how it's happening, but you will not need to know this mechanism. But we have seen many uses for the diazonium ion because that carbocation on the R group is readily formed as a result of losing our N2 as nitrogen. Remember, those are the Sandmeyer reactions. We could take a nitro group on a ring, reduce it to an aniline ring, then use our O-No reagent, HONO, to convert our NH2 into the diazonium, and then using different reagents, substitute that diazonium with different groups. Remember, if we wanted an OH, we do a certain recipe. We can add a chlorine or a bromine. We can add a nitrile. We can add a fluorine or an iodine. We can do a hydrogen, which is a deamination. We can remove the whole amine group. Or we can make azo dyes by complexing the N triple bond N with another aryl group, another aromatic group. That's an azo dye. Your book has an interesting section on azo dyes. They're easily made. They're actually one of the oldest synthetic organic molecules. They've been synthesized by organic chemists for a long time. They're called azo dyes. So to summarize the important reactions of amines, we had the Hofmann elimination, which was methylation of amines that gave us non-site-Ceph elimination. We also had the Hofmann rearrangement, which converted an amide into the amine, not by reducing the oxygen, but by excising the C double bond O. We did the cope elimination, which involved oxidation of the amine and then syn elimination of hydroxylamine to give a double bond. We did reductive amination, which was conversion of a ketone or aldehyde into an imine or an oxime, then followed by reduction of the imine or oxime to the amine. We did acylation, then reduction, which was conversion of an acid halide into an amide, and then reduction to the amine using something like lithium aluminum hydride. And we had the Gabriel synthesis, which was monoalkylation of phthalimide and then reduction of that to a primary amine. Basically, we pop that alkyl amine out of the phthalimide ring, either making the hydrazide or the diacid. So that's the end of lecture 13. That's the end of our organic lectures for this semester. If you want to work on this Dramatis workbook, it's chapter 27 for this material. We can also do practice problems on the board.